We're continuing to talk about zeros of polynomials. Where we left off last time, 3 weeks ago, was talking about the imaginary zeros theorem, and we learned that our complex zeros always come in pairs. We're going to discuss a few more theorems today, because so far with each one of these problems, we've been given something to get us started with. Either I've given you some binomials and I've said, check, see if these are factors, or I've said, hey, here is a factor, find the rest of them. By the end of this section, I'm going to be giving you nothing and just say, here, factor this giant polynomial or solve this high degree polynomial equation. So we need some more tools to be able to accomplish that. Our next theorem is the fundamental theorem of algebra. Yes, it's as important as its name leads you to believe, but it's something that we kind of take for granted. The fundamental theorem of algebra says that every polynomial of degree 1 or greater has at least one zero in the complex number system. Well, a polynomial of degree 1 or greater means that there's a variable involved. Degree 0 is just a constant. Degree 1 is x to the first, so it's something x to the first or higher. So basically, it just means that there's a variable involved. Every polynomial that has a variable has at least one zero in the complex number system. So basically, it's saying that if there's a variable there, you're going to get an answer. It might be real, it might be purely imaginary, it might be complex, which seems sort of trivial. We take for granted that if there's an x, we're going to get an answer, but it really was a huge deal that that was proved mathematically when it happened. All right, so that's one that we're kind of just tipping our hat to, but not one that you're going to use in practice. It's just one you're kind of taking advantage of. Our next theorem is our n-zeros theorem. And this is another one that you've been using, you just didn't know it was a theorem. This says that every polynomial of degree 1 or greater, so again, there's a variable involved, it can be expressed as the product of n linear factors. Hence, the polynomial has exactly n zeros, although some of those zeros might repeat. Well, again, we've been using this. When we're solving an equation and it's x to the first, we know that we're going to get one answer. When we're solving a quadratic equation, we know we're going to get two answers. A cubic equation, we're going to get three answers. It's the n-zeros theorem that we were using all that time to help us. So that's another one. We're going to use a little bit just when I see a 6th degree polynomial, I know I should have 6 zeros or 6 factors. The one that's really new for us is next, the rational zeros theorem. This is also sometimes called the rational root theorem or rational root test. This says that if we have a polynomial function with integer coefficients, then every rational zero of the polynomial has the following form. Now I want to pause for a second and just talk about what a rational zero even is. The word rational in math just means a fraction. And if you think about your types of numbers, right, real numbers, and then we break it up into rational and irrational numbers. Irrational numbers are non-repeating decimals, and rational numbers are things that can be written as a fraction. So every rational zero, these are real zeros that can be written as a fraction. So no square roots or anything like that. All right, so all the nice zeros are going to have the following form. We're going to take the factors of the constant of our polynomial and divide them by the factors of the leading coefficient of our polynomial. We're going to get this big, long list, and then we're going to test those zeros. So we get this weird fraction. We're going to simplify the fraction into a nice list, and then we're going to test those numbers in the list to find actual zeros. Not every number in our list is going to be a zero. It says possible rational zeros. We might get a list of 20 and it only be a cubic polynomial, So clearly, if it's degree 3, we're not going to get 20 zeros. So let's see how we use this rational zeros theorem. We want to list all the possible rational zeros for p of x equal to 6x to the third plus x squared plus 5x minus 2. We're going to start by making this weird fraction. In the numerator of this fraction, we're going to write all the factors of our constant term, which is -2. So what are our factors for -2? Oh, I need you guys to answer. This is going to be way too boring if I'm just talking to myself for like.
2 times -1.
Right? So to get 2, it's 1 times 2, but since it's a -2, it could be +1 times -2 or -1 times +2. So our factors are actually plus or minus 1 and plus or minus 2. In the denominator of this fraction, we want all the factors of our leading coefficient. So what are the factors of 6?
2 times 6.
All right, we could have 1 times 6, or we could have 2 times 3.
Yeah.
And we're getting to a +6, so it could be a +1 times a +6, or it could be a -1 times a -6. So when we list the factors in the denominator, they're also all going to be plus or minus. Any questions so far?
No.
On just where we're getting those numbers?
So we're only getting the zeros from the first and last.
Well, they're not the
Numbers.
zeros, they're just the factors.
Oh, okay.
So factors of 2 in the numerator, factors of 6 in the denominator.
Okay. And it's always going to be the first number in the denominator and the last one in the.
You are correct.
Okay.
Anybody else? Now we want to clean up this gross fraction into a list of like numbers that look normal to us. The first thing I want to do is address all these plus or minuses. We have a plus or minus in the top divided by a plus or minus in the bottom. A plus or minus divided by a plus or minus is actually a plus or minus. And if you think about it, it makes sense, because if I take like, the positive and the positive, I'm going to get positive. If I take the negative and the negative, I'm going to get positive. If I take the positive from the top and the negative from the bottom, that'll be negative. And if I take the negative from the top and the positive from the bottom, I'm going to get a negative as well. So I still get a plus and a minus. And when we simplify this, every one of our answers is going to be a plus or minus. So I usually just write plus or minus and then like a big parenthesis. All right, now we want to simplify this list. I encourage you to do it in a very systematic way so that you don't miss anything. So I'm going to start with the first number in the numerator, and I'm going to take it over every number in the denominator. So 1 over 1 simplifies to be 1. 1 over 2 is a half. 1 over 3, a third. 1 over 6, 1/6. And then I'm going to move on to the other number in my numerator. I'm going to take the 2 and then pair it up with each one in the bottom. So 2 over 1 is 2. 2 over 2 is 1, but 1's already on the list, so I'm not going to repeat it. 2 over 3 is 2/3. And then 2 over 6 simplifies to be 1/3, which is already on my list. So that's it. They're my list of possible rational zeros. Now, if I'm asked to find all the zeros for that p of x, I know to start by checking these 12 numbers. There's only 3 zeros since it's degree 3, but I'm going to get a start with these 12. And you may be thinking, Allison, that's like so many numbers to check. Well, we just went from infinity to 12. So I think we've narrowed the list pretty substantially. All right. So in the next one, I'm asking you to find all of the zeros of this polynomial. We want to start by creating our list of possible rational zeros, and then we're going to have to just use synthetic division over and over and over again to test and see which ones work. Possible rational zeros. I typically abbreviate it PRZ because that's just a lot to write. And we want all the factors of our constant divided by the factors of our leading coefficient. So what are our factors of 12?
Plus or minus 1, plus or minus 12.
1 and 12. But we need them
6
all.
and 2.
6 and 2.
4 and 3.
And 4 and 3. And even here, like I'll probably just stick the plus or minus out in front because I don't need to write it every time. I know in the end it's all going to be plus or minus. And then in the denominator, we're putting the factors of our leading coefficient. Our leading coefficient is 1, so that's nice. Just 1. And we want to clean up this list and do like a normal list of numbers. We know everybody's going to be plus or minus. And each number in the numerator needs to be put over 1. Anything over 1 is just that thing. Our list to check is going to be plus or minus 2, 3, 4, 6, 12. You do not have to put that in increasing order. I just put it in increasing order usually at the end because when I'm trying to choose which numbers to pick, sometimes it helps me as an individual to have them in increasing order. So I don't know. I feel like I could see better. Questions on getting our list of possible rational zeros? All right, well, now it's time to check them. What do you want to check first? Which number?
1.
You said 4?
1.
Oh, 1. Okay, so let's check 1. We're synthetically dividing it in. How will I know if it's a 0? Like, why am I doing this? I forget. It's been 3 weeks. I don't remember. Why am I doing this?
The remainder is 0.
If the remainder is 0, then that means that this number is 0. So we're just going to use synthetic division to check the remainder. We get a remainder of 0, so that tells us that 1 is a 0. The best way to find all the zeros is to get your polynomial in factored form. That's another reason I prefer to do the synthetic division rather than just remainder theorem, because remainder theorem gives us the remainder, but it doesn't help us with the factoring process. Remember that remainder theorem is where you just take whatever number is that you're checking and you plug it in for x. And if you end up getting 0, then you know that that is a factor. When we first talked about remainder theorem, I mentioned that I don't really use it. I only use it a little bit. I use it to check the number 1. See, if you plug 1 into this polynomial for x, when you raise 1 to any power, you get 1. And then we're taking that 1 and we're multiplying it by the coefficient. So really, we only have the values of the coefficient. A real easy way to check 1 using remainder theorem is to simply add up all of the coefficients. And if all the coefficients add up to be 0, then you know that 1 is a 0. So I use remainder theorem for 1 a lot, but that's kind of it. All right, let's get to factoring this. F of x. If 1 is my 0, what's the factor?
X minus 1.
X minus 1. And what's the degree of our next factor going to be?
Two.
It's going to be degree 2 because we had a cubic and we divided it by a first degree, so it's going to leave us with a quadratic, and right there are the coefficients for our quadratic, x squared minus x minus 12. Once you get down to a quadratic, you actually don't have to check possible rational zeros anymore because we're very versed with dealing with quadratics. We can try factoring it by the factoring techniques that we already know, or if it doesn't factor, we can always use quadratic formula to find the zeros. But this one factors nice. X minus 4 times x plus 3. So that's the factors, but the question is, what are the zeros? And we should get 3 of them. What are those 3 zeros?
1, 4, negative 3.
There we go. Questions?
Wait, I'm confused on how you knew 4 and 3 were.
I was looking for 2 numbers that multiplied together to be a negative 12 and added together to be a negative 1.
Okay.
Anybody else? By the way, I talked to Victor yesterday, who is one of the tutors that maybe you've dealt with in the York Tutoring Center, and I know that he's doing that online tutoring that I was showing you. So I asked him, because he's in one of my classes, how it was going and were students coming. So he said the other day he only had 1 student all day came and asked 1 question. So don't shy away from that virtual tutoring in case you think it's going to be swamped, because certainly right now it is not swamped. So I would encourage you to take advantage of that if you feel the need to talk to the tutors. I will continue to ask him questions to monitor how it's going and if there's better times a day, so that if you do want to use that service, that you know when are the best times. Okay. All right, so now we have this list of possible rational zeros. And so far our lists have been pretty small, like 12 numbers. But sometimes if your leading coefficient is 48 and your constant is 144, you could get these lists of, seriously, hundreds of numbers. Don't worry, I'm not going to do that. But you could get this huge list. So we need a way to kind of narrow down the list and make more educated choices so we're not doing division 100 times. So I'm going to show you 2 different techniques that can help us narrow down the list. The first one's called Descartes' rule of signs. So I'm going to read it to you and then I'm going to translate it for you. Descartes' rule of signs says if a polynomial function has real coefficients and the constant term is not 0, then the number of positive real zeros of the polynomial is either equal to the number of sign variations of p of x or less than that by a multiple of 2. The number of negative real zeros of the polynomial is either equal to the number of sign variations in p of negative x or less than that by a multiple of 2. All right, let me explain all that. Now, we're finding zeros here, and we could either have zeros that are real or zeros that are not real. Those are kind of the 2 options, real or not real. And we're going to call the not real ones complex. So we've got our real ones and we've got our complex ones. Well, then we could be more specific about the real numbers, and we could say positive real numbers and negative real numbers. what we're going to be doing is we're going to be making like a table, a chart, to help us conclude all of the possible combinations of positive real zeros, negative real zeros, and complex zeros. And then this table will help us make better choices between positive or negative numbers out of our list of possible rational zeros. So our rule of signs here says that the number of positive real zeros is either equal to the number of sign variations in P of X, and a sign variation is just when we're switching from plus to minus or minus to plus. So we're going to count the number of sign changes in P of X, and that's going to be the number of positive real zeros we have, or it could be less than that number by a multiple of 2. Similarly, to determine the number of negative real zeros, we first need to find P of negative X. Like plug negative X in for X and clean it up. We're going to find P of negative X, and then we're going to count the number of sign changes in P of negative X. The number of negative real zeros is either equal to that number, or again, less than that by a multiple of 2. You'll notice that both of them say or less than that by a multiple of 2. And where that's coming from is the possibility of there being complex zeros. We know that complex zeros always come in pairs by our imaginary zeros theorem. So we're subtracting out 2's because we're subtracting out the possibility of there being complex zeros, which always come in 2. All right, let's see one in action, and then hopefully that'll reinforce all that stuff I said. We're determining the possible combinations of zeros for P of X equal to x to the 4th plus 2x to the 3rd plus x squared plus 8x minus 12. So I'm going to make a table. The first column is going to be positive real zeros. The next column is going to be negative real zeros. And our third column is going to be the complex column. In the beginning, we're just going to work with the first 2 columns, and we'll figure out the complex column at the very end. Our rule of signs says that the number of positive real zeros is equal to the number of sign changes in P of X, or less than that by a multiple of 2. So we want to look at P of X and see how many times does it switch from plus to minus or minus to plus. So how many times does it switch?
Just one time.
Just one time here at the end, right? Now, I'm not going to fill in my chart. I'm going to put this number above my heading, 1. Oh, the number of positive real zeros is 1 or less than that by a multiple of 2. When we say the number of positive real zeros, we're talking about a quantity, not like the number 1. We're talking about a quantity of 1. And when we talk about quantities, we never talk about quantities in terms of a negative number. I didn't just go to the grocery store and go, damn, there's like negative 20 dozen eggs. There were no eggs. It's crazy. You know, we don't say, no, there's negative 2 gallons of milk in the fridge. Nobody talks about quantities that way. We either talk about it as a positive number or 0. We would say, I don't have any of something, so that would be a 0. So when we go to subtract less than this by a multiple of 2, we're going to take this initial number, which is 1, and we're going to subtract 2. If we subtract 2, we get negative 1. Well, it doesn't make sense to talk about a quantity in terms of a negative number, so that second option is not a viable option. That means that we're going to have exactly 1 positive real zero. No other option. Still not filling in my chart yet. Now I'm going to do the same thing for my negative real zeros. We need to look at the number of sign changes in P of negative X. So we actually need to find that. And then we'll simplify. A negative raised to the 4th power is positive. A negative x raised to the 3rd power is negative times that positive 2 is going to be a negative 2x to the 3rd. Negative x squared is going to be positive, so plus that positive. And positive times a negative is negative. And then our minus 12. So there is P of negative x. How many times does that change signs?
3.
Right? Yeah, I'm seeing 3 times as well that we're switching between plus and minus. So up at the head of above negative real zeros, I'm going to put 3. Because Descartes tells me that it's going to be 3 or less than that by a multiple of 2. So I'm going to subtract 2 from 3. I get 1. Is 1 a number that makes sense when we're talking about a quantity?
Yes.
Sure it does. So that's going to be a second option. I'm going to subtract 2 a second time. That gives me negative 1. Negative 1 is not a number that makes sense when we're talking about a quantity. So I'm going to back up, and it's just going to be 3 and 1 as my possibilities for negative real zeros. We're ready to fill in our chart now. We need to do every possible combination of our options for positive reals with our options for negative reals. So I always think of it, I know it's not the right word, but I always think of it like I'm distributing, like just to make sure that I hit every possible combination. We're going to have 1 with 3 and then 1 with 1. Last thing we're going to do is fill in our complex column. Our n zeros theorem told us that the number of zeros we have is equal to the degree. So each of these rows must add across to be the degree. And we just figure out what number that would be. Okay, because this is like option 1, option 2. Each row has to add across to be the degree, which is 4. So what would we have to add in our first row, right? What would the number have to be for complex so that we add it across to be 4? Well, 0, because I've already taken up the 4 zeros by having 1 positive real and 3 negative real. In our second option, we have 1 positive real and 1 negative real. So how many complex would there have to be? 2. When making my chart, I always double check when I'm done to make sure that all of my numbers in the complex columns are multiples of 2. We know complex zeros come in pairs, so I always make sure that I didn't make a mistake and I have multiples of 2 there. All right, so this is our chart. What does it tell us? We're really just focusing on the first 2 columns of the chart, since the numbers that we're checking are possible rational zeros are positive or negative real numbers. So I'm really just looking at the first 2 columns. The first thing I'm doing is I'm looking for which column has the most zeros in it. If there is a column that has zeros in it, I'm going to avoid that type of number. So for instance, if this was a 0 here, it's telling me that there aren't any positive real zeros. So I'm not going to waste my time when I'm checking that list. I'm not going to waste my time checking positive numbers. I'm only going to check negatives. Even if there was only 1 0, I would still avoid checking positives. I would start with checking negative numbers because it's a 50-50 chance that there aren't going to be any positives, but there's a 100% chance that I'm going to get a negative real zero, so I would definitely start by checking negative numbers. If neither of these columns have zeros in them, then I'm going to start with the type of number that has the biggest numbers in that column. So I would start in this example by checking the negative numbers in my list of possible rational zeros, because I could have up to 3 of them, whereas I'm never going to have more than 1 positive. Questions? And don't worry, we're going to do it again. So if you're like not quite sure what to ask, or if you have a question yet, we'll be seeing this again today, so you'll have that opportunity. Does anybody have anything right now? Okay. We have another thing to help us. It's our rules for upper and lower bounds. So f of x is some polynomial with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. All right, now Descartes' rule of signs you're going to do before you start checking zeros, because it's going to tell you which numbers to pick in the list. These upper and lower bounds, you're going to use these rules when you're in the division. Like, you did the division and you didn't get a remainder of 0. What information can I get out of my, I don't want to say bad answer, but my division that did not produce a factor? So if what you're dividing by is greater than 0, if it's positive, and each number in the last row is either positive or 0, then C is an upper bound for the real zeros of F. So say I'm doing division, I had a 5, and I ended up with this as my bottom row. 4 was my remainder, so this wasn't a factor, all right? But since what I divided by was 5, and all the numbers in the bottom row were positive, so positive on the outside, all positive on the bottom, tells me that 5 is an upper bound, which means don't check a number bigger than 5. You need to check a number smaller than 5, because none of the ones bigger than 5 are ever going to work. Then we have a rule for the lower bound. If what you're dividing by is negative, less than 0, and the numbers in the last row alternate positive and negative, maybe there's a 0 thrown in there, then C is a lower bound for the real zeros of F. So we might have something like, maybe we're dividing by -2, and then our last row is 4, -1, 3, -2. Then this would tell us that -2 is a lower bound, and we should check a number larger than -2 in our list. I didn't used to use this so much, but now that I teach it all the time, I find that it's more and more helpful, and I probably could have used it more when I was a student. All right, well, let's take everything that we have talked about and put it into one giant problem. That's going to take me like 20 minutes. Here goes. If you need a drink, go get one. It's going to be 20 minutes. All right, so here we have this 5th degree polynomial. P of x equals 2x to the 5th minus 5x to the 4th minus 5x to the 3rd plus 25x squared minus 7x minus 10. We're going to use Descartes' rule of signs to determine the possible combinations of positive real zeros, negative real zeros, and imaginary zeros. Then we're going to use the rational zero theorem and determine the possible rational zeros. Then we're going to look at the chart. We're going to figure out which of those possible rational zeros we should start with. And then we're going to start testing those possible rational zeros and ultimately rewrite this polynomial function as a product of 5 linear factors. Remember, whatever the degree is, that's how many linear factors we should get by our n zeros theorem. All right. First thing we're working on is our chart. I hope that heading's okay. Positive real, negative real, complex. If you need to write out the words for right now, then I would encourage you to do that. We start by looking at the number of sign changes in our P of X. Looking at P of X, how many times do we switch from plus to minus or minus to plus?
3.
3 times. So that's going to be my first option for positive is 3, but it could be less than that by a multiple of 2. So I'm going to subtract 2 from 3 and I get 1. Is that an okay number for a quantity?
Yes.
Sure it is. So I'm going to add that to my list of options. I'm going to subtract 2 a second time. I get negative 1. Is that an okay option?
No.
No, it's not. Can't have any negatives. So I'm going to stop there. Those are my only 2 options. Next, to determine for the negative real zeros, we have to look at P of negative X. So we need to find it. There is a little shortcut to finding P of negative X. Because of the whole even odd rule, right? Taking a negative and raising it to an even or an odd power. Hold on, I can't write this and talk at this. Because of the whole even odd rule, when we raise the negative to an even power, it turns positive. And then when we multiply it by the coefficient, we're going to get whatever the sign of the coefficient was. When you take the negative and raise it to an odd power, you get a negative. And then you're going to multiply it by the coefficient. You're going to end up with whatever the opposite of the coefficient was. So the shortcut, if you care to use it, is all we do to go from P of X to P of negative X is change the sign of the odd degreed terms. Because the even ones will stay the same, because when we square a negative, we get a positive. So we're left with the sign of the coefficient, but the other ones are going to switch. And shortcuts are only good if we get them right. So if it doesn't make sense to you, then please just do it out the way that you've always done it. We look to see how many times we change from positive to negative or negative to positive. I see
Should be 2, right?
1, 2. Yep, I see 2 as well. All right, so that's our first option for negative real zeros. It could be that number, or it could be less than that by a multiple of 2. So if I subtract 2 from 2, I get 0. Is that a number that makes sense when we're talking about a quantity?
Yes.
Sure. Those 0 is a second option. We subtract 2 a second time, we get negative 2. Does that make sense?
No.
No, it doesn't. Can't have our quantity in terms of a negative number. So I have 2 options for positives, 2 options for negatives. Now I just need to do every possible combination. So this is like a real foil, I think. So I'm going to do 3 with 2 and then 3 with 0. And then I'm going to do 1 with 2 and then a 1 with 0. So this chart, man, we have 4 different options for the combinations of zeros. We need to fill in our complex column. We fill in our complex column with whatever number makes it so that each row adds up to be the degree, and our degree this time is 5. So every row needs to add up to be 5. So what number should we have in our complex column?
0.
2. Yeah.
Another 2, and then lastly
4.
4. So there we go. There's our chart. So what does this chart say to me?
I'm a little, oh, sorry.
No
I'm a
problem.
little confused with the complex, how we get the complex.
Okay, each row has to add across to be the degree. So in the first
Oh.
row, I already had 3 and 2, which adds up to be 5. So I don't have any left that could be complex. And then
Okay.
in the next one, I have 3 positive and no negative. So that's only a total of 3. I need 2 more to make it 5.
Okay.
Anybody else? Okay, so interpreting this chart, you'll notice that our negative column has 2 zeros in it. 2 out of 4 of my rows have zeros in it, which means it's a 50% chance that there aren't going to be any negatives at all. But in my positive column, I have a number other than 0 for every single option. I personally would definitely start with positives, because it's 100% chance that I'm going to get a 0, but only a 50% chance that I'm going to get a negative real 0. But honestly, you don't even have to like look at the chart. Just make the chart, and then if you feel like you have trouble interpreting the chart, you honestly can just go through the list and not use it. Next up, we want to list our possible rational zeros. This is the factors of the constant divided by the factors of the leading coefficient. And we also remember that everything ends up being a plus or minus. In the numerator, we want the factors of our constant. What are our factors of 10?
1 and 10.
And 2 and 5. And then we have our factors of our leading coefficient 2. That's just 1 and 2. And now we want to clean this up into like a normal list of numbers. Everybody's going to be a plus or minus. And to simplify it, I'm first going to take every number in the numerator and put it over 1. We know anything over 1 is just that thing. So 1, 10, 2, 5. And then I'm going to take every one of those numbers in the numerator and put it over 2. 1 over 2 is a half. 10 over 2 is 5, already on my list. Two over 2 is 1, already on my list. And then 5 over 2 is 5 halves. So there we go. There's our list of possible rational zeros. Now it's time to start testing those numbers so that we can rewrite our polynomial as the product of 5 linear factors. I always check positive 1 first. And the reason I check it is because I use remainder theorem for it, where I just add up all the coefficients of our polynomial. So if we add these up, so the positives are going to be positive 27. -5, -10, -20, -27. So I see that I get 0 just by adding up the coefficients. That tells me that 1 is absolutely going to be a 0, so I'm going to start with +1. Again, you don't have to do that. You can just start with your synthetic division. I just like to point out kind of what I think are good shortcuts here and there, but you don't have to use them. Definitely make sure that you're not writing huge. So let's divide. And we get our remainder of 0. And we should be anticipating that there would be a remainder of 0 because we knew that 1 was a 0. So when we divide, we should get a remainder of 0. Well, this is great because now we can start factoring our p of x. If 1 is a 0, what's the factor?
X minus 1.
X minus 1. What degree is the next factor going to be?
4.
4th degree, because we had a 5th degree and we divided it by a 1st degree. I'm going to be left with a 4th degree, and there are my coefficients. Great. We're on our way. Now it's time to pick another number out of our list of possible rational zeros, and we're going to synthetically divide it into this 4th degree polynomial, because remember, we're trying to continue to break it down into the product of linear factors, so we don't go back to the original, we go to the next largest factor. So what number out of our list would you like to check for, see if it's a 0? What would you like to check next?
2.
2. And this is where problems can like get long or short. Sometimes you guess lucky and you just happen to pick the right numbers right away, and then sometimes you check 10 numbers before you find one that works. Sometimes it's just the luck of the draw. Well, remainder of 20, so that didn't work. Let's pick something else.
Ten.
I'm not feeling good about this one. But it does give me the opportunity to point something out to you. Notice that 10 is positive and all the numbers in the row, in the bottom row, are positive. This tells us that 10 is an upper bound. Now I know it is the biggest number on our list, so of course it's our upper bound, but here we can see that rule kind of in action. So positive that you are dividing by, everything's a positive on the bottom, upper bound. All right, let's try something else. For the sake that I'm running out of room on my page, I'm going to pick a number. Now, notice we're checking positives because our chart said to check positives, but it is possible that we only have one positive. Let's go back and look at this number 2 here that we checked. Notice how at the very end it was 10 plus 10. Like, man, it was so close. If that 10 was just a minus, we would have had a 0. So I'm going to switch. My gut tells me to switch and check -2. Since positive 2 was super close, maybe it is -2 that ends up working out. So just because when we looked at our chart, we said, hey, I think I'm going to start with a positive, doesn't mean that you got to stay with that until you check every single positive. So there we go. We got remainder of 0. So that tells us we have another 0, and if we have another 0, we have another factor. So let's get back to factoring this P of X. We have X minus 1 from the beginning. What's the next factor going to be? We have go ahead, I'm sorry.
X plus 2.
X plus 2, we have a 0 of -2, so our factor is going to be X plus 2. What's going to be the degree of our next factor?
3.
Third degree, because we were breaking down a fourth degree. We divided it by a first degree. We're going to be left with a third degree, and there are our coefficients at the bottom. (2x to the third minus 7x squared plus 6x plus 5). So notice that we're now down to a cubic, and that cubic has 4 terms. We're just learning additional new techniques for factoring. It doesn't mean that everything we already know for factoring isn't true. So as soon as I get down to a cubic where there's 4 terms, I try to factor by grouping. Now, it doesn't work in this example, but I'm going to be super happy the times that it does work because it's going to save me from checking a whole bunch of zeros. So just be mindful of that. Don't forget techniques that you've already learned. So far we have 1 positive real 0 and 1 negative real 0. If I go back to my chart, that means that this option and this option aren't options because they said we wouldn't have any negative real zeros. So now looking at my chart, what does it tell me?
The other number is negative.
There's definitely a second negative number. So I would switch my focus to the negatives. It's only 50-50 whether there's going to be any more positives, but I'm guaranteed a second negative. So let's try another negative number. And I'm going to recommend -1/2. Sorry, I won't be there to offer recommendations to you when you're working on your homework. I also want to mention it's super important. Synthetic division does not work if you're missing a term. You have to put in a placeholder. I've seen students where they come in telling me that they've spent 2 hours on a problem and they've done all this division and nothing works. And I point out to them that they needed to include a placeholder in their dividend, and then it worked right away. So remember, synthetic division, if you're missing a term, you must put a placeholder in every time. We've got another remainder of 0, so that means that I have another factor. -1/2 is my 0. So x plus 1/2 is my factor. And then our next factor is going to be quadratic. 2x squared minus 8x plus 10. Questions so far? Okay, well, once you get down to a quadratic, you can stop checking zeros because we're going to be able to factor this using techniques we've already learned, or if it doesn't factor, we'll be able to use quadratic formula to find the zeros, and then we can work backwards from the zeros to the factor. So is there anything we can do to factor that 2x squared minus 8x plus 10? Don't forget your very first factoring technique, which is GCF. We can factor a 2 out of that. Leaves us with x squared minus 4x plus 5. I think of two numbers that multiply together to be positive 5 and add together to be negative 4. Unfortunately, nothing works. So we are going to have to use quadratic formula to get the zeros, and then from the 0, we'll work backwards to the factor. All right, so quadratic formula. X equals negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1. So that's going to be 4 plus or minus the square root of 16 minus 20 over 2. It's going to be 4 plus or minus the square root of negative 4 all over 2. We know that the square root of negative 4 is equal to 2i. And then we'll break it up into two separate fractions and simplify and get 2 plus or minus I. To get the factors, I'd definitely break this up into two separate zeros. X equals 2 plus I, and then x equals 2 minus I. To go from the zeros to the factor, all we do is move it over. And when we move it over, we know the signs change. This becomes x minus 2 minus I. So that'll be one of the factors, and then x minus 2 plus I. And this will be the other factor. So almost there, ready to write our grand final answer. P of x equals 2 times x minus 1 times x plus 2 times x plus a half times x minus 2 minus I times x minus 2 plus I. And there we go. And that was awesome. I hope you feel super accomplished. Questions? What questions do you have?
How long do you upload this again?
Say that again? Say that again, Nathan.
How long till this will be uploaded? Because I'm gonna have to look over this again.
Okay, so I'm gonna have to make a special link to put it in your class. So probably an hour or two. It just, the processing takes time. And I can even get it up on YouTube, but then YouTube has to take its processing time. Don't worry, we're gonna do more next week. I know it says on our calendar we were gonna be done with this today, but that's not happening. So I hate to even start another one because clearly it takes 20 minutes, but we'll do another one on Thursday. Then we're gonna solve an equation. And then we're gonna look at some application problems. You know what, we can do this equation. This won't take very long. We'll do this one more today. But this is like a super powerful technique, our ability to solve high degree polynomial equations, because that's why we learn how to find zeros and to rewrite things as factors, is so that we can solve equations, and we solve equations so that we can apply application, solve application problems. So let's solve the equation 4x minus, x to the fourth minus 4x to the third plus x squared plus 12x minus 12 equals 0. Since the directions didn't say use Descartes' rule of signs to list all the possible combinations, personally, I'd skip the chart. Maybe if I was super stuck, I'd do the chart, but otherwise, I'd just skip it. And it didn't say that I had to list every possible rational zero, so probably I would just list some of them and then check them, and if those didn't work, then I'd try a couple more. 12 and 1 are pretty small, so I might be inclined to list all possible rational zeros, but you don't have to if the directions don't indicate that. Or positive rational zeros, factors of 12, 1, 2, 3, 4, 6, 12. Divided by the factors of our constant, which is just 1. So we get these numbers right here, plus or minus 1, 2, 3, 4, 6, and 12. And then we start checking numbers. As I mentioned before, 1 is always my first go-to, because all I have to do is add up the coefficients. Add the coefficients this time, my positives. 1, 1, and 12. So that's going to be what, 14? And then the negative ones, that's negative 16. So I don't get 0. So that tells me that 1's not going to work. So I'm going to check something else. What number would you guys like to check first?
-1.
Let's check -1. Got a remainder of something other than 0, so that one doesn't work. Let's try something else. How about, I don't know, 2? And I usually do start with small numbers. And I usually start with positives just because I'm less likely to make a sign error. And this time we get a remainder of 0. So that tells us that we have a factor. And I can start factoring my equation. It's going to become x minus 2 times, our next factor is going to be cubic, x to the third minus 2x squared minus 3x plus 6, and we're still equal to 0. If you recall what I said in the last example, that once I get down to a cubic with 4 terms there, I totally try to do factor by grouping. And you'll notice this time that when we do factor by grouping, it works. This factors into x minus 2, and then x minus 2 times x squared minus 3 equal to 0. So look at that. For the first time, we've gotten a factor that with multiplicity to it, where it showed up multiple times. I'm so happy I saw that factor by grouping, because we would have checked every single solitary one of those possible rational zeros, and none of the rest of them were going to work. If that ever happens, where you found 1 or 2 that have worked, and then you check all the rest and none of them work, but you're not getting down to a quadratic that you can use quadratic formula on, try checking one that already worked a second time, because you might have a 0 with multiplicity to it. Remember that our objective in this example is to solve the equation, not necessarily rewrite it as a product of linear factors. So once I get down to this quadratic, I'm just setting every factor equal to 0 and solving. We get x equals 2, x equals 2. Which technique would be easiest to solve this quadratic? Something squared and a constant? Square root property is always the easiest way to go. So I'm going to isolate what's being squared, and then take the square root of both sides. We get x to be equal to plus or minus the square root of 3. Our degree was 4. We got 4 answers, even though 2 of them were the same. But we got 4 different zeros. So that still supports our n zeros theorem. See, so it's not so bad once you get going. That first one just had so much in it, and that was our first time through, so it takes a long time. But just like factoring, that once you start doing some of these, you're going to get much faster because you know what to do and you have better instinct. Any questions on this one? Okay, well, work on your My Math Lab, and like I said, I will post this recording, but there are also still my short, concise recordings. If you don't want to listen to this long one again, my short recordings are still posted on D2L like normal, and still don't have a take-home quiz due yet because I didn't get through this. So it'll probably be due next Wednesday. I'll let you know on Tuesday for sure. You do have all the skills you need to finish that. I think it's 3233 take-home quiz, but it'll be due on Wednesday. If anybody has any questions about anything, let me know. Also, if you did not finish that survey I sent out about office hours, please do that like right away, because I want to get a decision on office hours and get that posted out as soon as possible. Anybody, anything before we go?
Nope.
All right, have a wonderful weekend.
You too, thanks.
Let me know if you need anything.